We can begin.
Welcome everyone to the second CSE Online Theory Seminar. Today we have Dr. Subrahmanyam from our own CSE department, and he's going to tell us about the sensitivity conjecture, which was recently resolved. Technically, it's maybe now the sensitivity theorem or something, and it has a very short, elegant proof, and he'll tell us more about this. Subra.
Thanks, Karthik, for introducing me. So please interrupt me if there are any questions at any point. So as Karthik said, this was a famous conjecture which remained open for about 28 years or so, and was resolved last year. And actually, Aravind suggested me to talk about this particular topic, and I was very eager to talk about this once he gave me the suggestion. Yeah. And this is Hao Huang, who is a mathematician at Emory, and he is he resolved the sensitivity conjecture. So in July last year, he put out the proof, and it attracted wide attention in all the blogs and Twitters of computer science people and also mathematicians. I just want to say some of the slides that I am using are kind of adapted from a presentation that Huang made in a talk. Yeah. Right. So I'll just first I'll present a combinatorial question. Again, if there are any issues about hearing me or not able to hear me, please let me know. I'll try to speak loud. I don't have very highly specialized equipment for recording. Okay, so first a combinatorial question, and first we'll see how. So the thing is that the sensitivity conjecture is actually equivalent to this question, but I'll first state this question in the combinatorial version, present the entire proof, and then after the proof, show the connections or show how sensitivity conjecture is related to this. Okay. So if you listen to if you see this question independently, it may seem like it is unrelated to the conjecture because it is unrelated to anything in complexity theory. Yeah. So the Boolean hypercube is a graph on all the n-bit vectors, n-bit binary vectors, and what I've shown here is the three-dimensional Boolean hypercube. There are 8 vertices, one for each 3-bit vector. And 2 vertices are adjacent if and only if their Hamming distance is exactly 1. So you can see here the vertex 0, 0, 0 is adjacent to the vertex 1, 0, 0, 0, 0, 1, and 0, 1, 0. So all of which are obtained by just changing one input value, one of the input coordinates, right? So the question I want to first ask is, now I have colored 4 of these vertices red, right? And these 4 form an independent set, right? And this is the case with Q3, which is a 3-dimensional hypercube. But this is also true for any Qn, any n-dimensional hypercube, simply because the hypercube is a bipartite graph. And basically all the vertices with odd parity, odd number of ones in it, are on one side, and all the vertices with even parity are on the other side, right? So here I have picked simply the vertices with the odd parity to be the red vertices, and these form an independent set. And obviously, the graph induced by the red vertices has degree 0 on all the vertices. So the question is, we are interested in what happens when we pick one more vertex. Okay, so this graph has 8 vertices. Now, if we pick a 5-vertex subgraph, 5-vertex induced subgraph, what can we say about the maximum degree of the 5-vertex induced subgraph? So we are interested in that quantity. So suppose we add one more vertex here to the 4 red vertices picked. You can see that whichever vertex we choose to add, for instance 0, 0, 0, this gives you a vertex of degree 3, right? If you make the 0, 0, 0 vertex red, then this vertex will have degree 3 in the graph induced by the 5 red vertices, right? Okay, so the question is, we want to pick 5 vertices in such a way that we want to minimize the maximum degree of the graph induced by these 5 vertices. So, and if you add any of these white vertices and you make them red, it gives you a vertex of degree 3, which is not that good because the Q3 graph itself has max degree 3. But there is another way to choose 5 vertices such that the max degree is 2, like in the figure we have here. The max degree here is 2. If you look at the graph induced by the red vertices, there are 5 red vertices and they form an induced path of length 5. Right? We can even include the top top right vertex. This forms a 6 cycle, and even this has max degree 2. Right? And in fact, you can play around with this and see that whichever 5 vertices that you pick, there exists a vertex of degree at least 2. Right? What about if you go to the next dimension, Q4? So this is Q4, the 4-dimensional hypercube. So I've drawn it as 2 Q3s, and I am making the adjacent making the corresponding vertices adjacent. So the Q3 here, so let's say the bottom left vertex corresponds to 0, 0, 0, and it is adjacent to the vertex here corresponding to 0, 0, 0. Okay, so you can understand how this is the Q4 graph. And again, I have colored 9 red vertices. And you can see that the 9 red vertices form an induced graph whose maximum degree is 2. So if it's difficult to see, now you'll be able to see this better. The selected vertices form an 8 cycle and an isolated vertex over here. Right? And whichever way you choose 9 vertices from the Q4, so 9 means 1 more than the half. Right? Whichever way you choose 9 vertices, you will get a vertex of degree at least 2. And this question can be asked for any Qn in general. So if you go to Q5, it turns out that you cannot pick, so there are 32 vertices in Q5, you cannot pick 17 vertices or whichever way you pick 17 vertices, you will get a vertex of degree at least 3. Okay. So the question is, what is the smallest possible value of the max degree of H, where H is an induced subgraph of the n-dimensional Boolean hypercube with exactly 2 power n-1 plus 1 vertices. Right? In other words, the second statement is easier for me to see and understand. What is the minimum over all H of this vertex size and of the max degree? So is the problem clear? Hope no questions. If you have questions, please interrupt me and ask the questions. Right? So this is what we want to determine. So what was known about this problem? Right? So let me mark this question as the start question. So in 88, Chung, Furedi, Graham, and Seymour had studied this problem. This was even before its connection to sensitivity was known. And they showed that every such H that you pick having 2 power n-1 plus 1 vertices, the maximum degree of the graph induced by those vertices is log n times a constant, right? So which means that the answer to the start question is at least log n, at least omega log n, right? And they also showed a specific H which has max degree square root n, which means there exists a induced subgraph of 2 power n-1 plus 1 vertices that has maximum degree square root n. Right? So this means the answer to the start question is at most square root n. Right? So we want to minimize the max degree of all H. So so we have an instance where the max degree is square root n, and we know that for all H the max degree is at least log n. Right. So this is what they showed, and this question also, which we'll see is kind of equivalent to sensitivity. This question also had remained open till now. So the answer to the start question could be anywhere between log n and square root n, right? And first I will very quickly explain the construction of the upper bound. So for this upper bound, it may be easy to assume that n is a perfect square. So you can partition n into square root n subsets, each of size square root n, right? And if you take the vertices of the hypercube, there is a correspondence between the vertices of the hypercube, which are the n bit vectors, and subsets of this subset of the set 1, 2, 3 up to n, right? Right. So you can view them as sets equivalently. You can view the vertices of the hypercube as sets. So let X be the collection of those sets or those vertices, which are defined here. So X is a set of all even sets that contain some of these Fi, and the union of all the odd sets that do not contain any Fi. So I'll explain a bit of the argument, and then it will be easy for you to see why this has degree square root n. So suppose X is a set of the former type, which is an even set that contains some Fi. Now, if you add an element to the set, right, or equivalently flip a 0 of the set to a 1, it will become an odd set, and it will still continue to contain that Fi. So which means it will become an odd set that is not there in X. So it does not contribute to the degree. So what if we remove an element from the set, which equivalently flip as 1 to a 0? So then we will again get an odd vector. Of course, it's a bipartite graph with even sets on one side and odd sets on the other side. So we will get an odd set. Now, if the even set contains two Fis, or two or more Fis, then the flipping of one bit will only remove at most one Fi. So it will still continue to contain the other Fi. So if the even set contains more than one Fi, it will still flipping 1 to 0 will still not give you a set in X. So what remains is the even sets that contain exactly one Fi. And in those, if you flip those ones that are in Fi, right, some element of Fi, it will no longer contain that Fi, which means it will no longer contain any Fi. And therefore, we will get an odd set that does not contain any Fi. So since it contains Fi, and Fi contains square root n elements, there are possibly there are at least square root n elements. In fact, exactly square root n elements to flip, 1s to 0s. So the degree of such an X from this even set collection is exactly square root n. You can make a very similar argument for the odd sets as well. So this shows that the degree of this graph is actually square root n. And you can do some inclusion, exclusion, and actually calculate the size of the set, and which is exactly 2 power n minus 1 plus or minus 1. I think when n is a perfect square, I think you always get plus 1. For more details, you can see the paper. Okay, so they showed the upper bound and lower bound not matching, and what Huang showed is that the upper showed that the answer to the star is actually equal to square root n, which means this is tight. Every Boolean, every H that contains exactly 2 power n minus 1 plus 1 vertices has an induced subgraph that contains a vertex of at least square root n. So which means they improved on the lower bound, and this is what we have. Right? Any questions till now? Hope things are clear so far. Okay. Okay, so now let's go to the proof of this result. Right? Again, I'm restating the theorem. So the first key observation is that let us look at the adjacency matrix of a graph. And the largest eigenvalue is upper bounded by the maximum degree of the graph. Why is this the case? Again, this is a somewhat of a standard fact, but I'll still write the proof because it's very short. So let V be an eigenvector corresponding to lambda 1. Right? So again, when I say the largest eigenvalue of A, it's the adjacency matrix which has of the graph. So it is an n by n matrix if the graph has n vertices. In the case of Qn, it has 2 power n by 2 power n matrix. It has a 1 if there's an in the ijth entry if there's an edge from the I to j, and it's a symmetric matrix. Okay. So let V be an eigenvector corresponding to the largest eigenvalue, and let Vi be the entry of V with the largest absolute value. Okay. Now look at lambda 1 times Vi. So what is lambda 1 times V? Lambda 1 is the eigenvalue and V is the eigenvector. So lambda 1 times V is nothing but A times V, because that is the eigenvalue, eigenvector property. So the ith coordinate of lambda 1 times V is nothing but the ith coordinate of A times V. And ith coordinate of A times V, you can just look at the ith row of A, the dot product of the ith row of A and the vector V. The ith row of A contains a 1 at the jth column if ij is an edge. So it is just the summation of all the entries of Vj where ji forms an edge, right? And the summation here has the degree of I many terms, which is upper bounded by the max degree of the graph. And each entry Vj is upper bounded by the absolute value of Vi by assumption. So we get that this is upper bounded by delta G times the absolute value of Vi. And now you can easily see that by cancelling the absolute value of Vi, we get lambda 1 is at most the max degree. Right? So here what we observe is that we wanted to show a lower bound on the max degree. And we are showing that the max degree is lower bounded by the largest eigenvalue. So now it is enough to lower bound the largest eigenvalue by square root n, right? So that is the first kind of observation. Instead of looking at the degree directly, we can look at lower bounding the max eigenvalue. Fine. So the second kind of idea is the theorem called Cauchy's interlacing theorem. So what is Cauchy's interlacing theorem? So it's a theorem for all the matrices, symmetric matrices of size m, and that A be such a symmetric matrix, and B be a principal submatrix of A. So what is principal submatrix? It's so let's say you pick the first, fourth, and sixth rows of A and the first, fourth, and sixth columns of A, and look at the submatrix formed by exactly these rows and these columns. So that is a principal submatrix. So basically you pick a subset of rows and the same subset of columns that forms a principal submatrix. So in such a case, then if the eigenvalues of A are lambda 1 to lambda n, and the eigenvalues of B are mu 1 to mu n, right? In such a case, each of mu I is upper bounded by lambda I, so and lower bounded by lambda subscript I plus n minus m. In other words, the ith largest eigenvalue of B is at most the ith largest eigenvalue of A, and jth smallest eigenvalue of B is at least the jth smallest eigenvalue of A, right? So is this clear? Why this is helpful is because we are looking at subgraphs, induced subgraphs of Qn. So in particular, we are looking at subgraphs on 2 power n minus 1 plus 1 vertices, right? So that will correspond to the induced subgraphs will correspond to the adjacency matrix will be a principal submatrix of the adjacency matrix of Qn. And the largest eigenvalue of the induced subgraph will be actually the 2 power n minus 1 largest eigenvalue of the adjacency matrix of Qn, right? So this part, this inequality gives us what we something in the direction of what we want. So the lambda, the largest eigenvalue of the subgraph is at least the 2 power n minus 1 largest eigenvalue of the adjacency matrix of Qn, right? So again, this slide I have explained it better. So lambda 1 of h by the interlacing is at least lambda 2 power n minus 1 of Qn. So I am kind of using Qn for both the graph as well as the adjacency matrix. So let's see what the eigenvalues of Qn are. The eigenvalues are n, n minus 2, n minus 4 up to minus n, each with multiplicity n choose 0, n choose 1, and so on till n choose n. So you can see that there are 2 power n eigenvalues. And depending on the parity of n, we get that the max degree of h is at least the lambda to the 2 power n minus 1 eigenvalue of Qn, which turns out to be 0 or 1 based on the parity of n. If n is even, I think we get 0. If n is odd, we get 1. But this is not enough for us, right? We were looking at a square root n lower bound. Any questions so far in the eigenvalue lower bound, or the degree lower bound by the eigenvalue and the interlacing theorem?
So for the original matrix, you want to look at the 2 power n minus 1 eigenvalue, right? Approximately.
No. You want to look at 2 power n minus 1 eigenvalue. Exactly 2 power n minus 1 eigenvalue. Yeah. I misheard you first.
Yeah. So we're saying that for lambda 1 we are not getting a tight bound, but perhaps for lambda 2 to n minus 1 we get a tighter bound in terms of the degree.
I didn't follow the tightness part.
For lambda 1, the bound is not tight, right? Because it's not giving us the original delta. Lambda 1 is much smaller than.
Yeah. So if you take the adjacency matrix of the original adjacency matrix, it does not give you what we want. Yeah. Okay.
And also we're looking at absolute values, right? Is that right?
Absolute values of what? So till now, the adjacency matrix is all positive. There is no absolute. Everything is positive.
No, the eigenvalues are all positive, is it?
Oh. No. It's not positive.
Not
but
positive.
So when I say
sorry, when you order the eigenvalues, you're ordering the absolute value or by the just
the actual value, not the absolute value.
Okay, sure.
So here I have ordered from n minus 2 and so on till minus n.
Okay, sure.
Yeah. Any other questions? Okay, so
Subru, question.
Yeah, please.
So Cauchy's interlacing theorem is valid for any two matrices, right? The entries need not be 0, 1 only.
It need not be 0, 1. Yeah. So
Okay.
it actually, one way to see it is if you know the max min characterization of the eigenvalues. So there is this Rayleigh-Ritz quotient. So you look at if you want to compute the kth largest eigenvalue of a matrix, you compute what is called the Rayleigh-Ritz coefficient. I don't have a slide for that. Where the vectors come from a k-dimensional subspace, and you find the smallest, the vector that minimizes this, and then you maximize over all the subspaces, all the k-dimensional subspaces. So there is this max-min characterization. And that gives you a very straightforward proof for the interlacing theorem.
Okay.
Yeah, this is one way to see it. Yeah.
Mm-hmm.
And in fact, there is a small, we can replace this. So if the interlacing theorem happens to be the most kind of sophisticated, if you can call it that, tool that we are using for the proof of the sensitivity conjecture. And even this can be replaced with a slightly simpler argument, or slightly without appealing to the interlacing theorem. So I won't really call it simpler. I found some interlacing argument easier to present. But I have a slide on the other argument which we'll see. Okay, so the point is that if you take the matrix of Qn, we don't get what we want. So the final ingredient is that instead of taking the adjacency matrix as it is, if you take a signed adjacency matrix, even then the result about the max degree being lower bounded by the lambda 1 holds. So if you take a graph and you change the signs of few entries in the adjacency matrix, the only thing is that we have to do it symmetrically. So if you change the ijth entry sign, the jith entry sign also has to be flipped. And then even for this adjacency matrix, the largest eigenvalue is upper bounded by the max degree of the graph. right? And the proof is exactly the same as before. So when you actually write down the same proof for this, now the absolute values are kind of required for you. For the earlier proof, the absolute values were not really required. So if you have a signed adjacency matrix and you look at the largest eigenvalue of the signed adjacency matrix, this inequality still holds. So if we can find a signing of the adjacency matrix of the Boolean hypercube such that the 2 power n minus 1th largest eigenvalue is square root n, then by interlacing we will be done, right? Because the submatrix will correspond to the signed adjacency matrix of H, and the largest eigenvalue of H will be at least the 2 power n minus 1th largest eigenvalue of the matrix M, and if you can show that that eigenvalue is at least square root n, then we are done. Clear? Okay, so all that, or to put it simply, all that Huang did was to find such a signing. And what is the signing? So just before going to the signing, I'll just describe the adjacency matrix of Qn, which I'm just using Qn itself to denote. So Q1, which is the one-dimensional hypercube, is just an edge. This is the adjacency matrix, and you can recursively define it like this. So basically, Qn has two copies of Qn minus 1, and the corresponding vertices are connected by an edge. So this is, if you recall, we had the Q4 constructed using two Q3s, and corresponding vertices were made adjacent by edges. So that the corresponding, these edges that are added are the off-diagonal identity matrices, and we have Qn minus 1, Qn minus 1 that represent the two Qn minus 1 that are in Qn, right? And the signing is just a small variation of this. So you start with the same adjacency matrix, and instead of doing this recursive definition, you just put a negative sign in the bottom right entry. So Mn is equal to Mn minus 1 identity matrix minus Mn minus 1. And you recursively make this construction. And it turns out that this matrix just works. Fine. Again, I have the definition here. So let's see why it works. So recall, all that we have to show is that the 2 power n minus 1 largest eigenvalue is square root n. So you look at the square of this, and the off-diagonal entries cancel out. And the diagonal entries are Mn minus 1 squared plus I identity matrix. By induction, we get that Mn minus 1 whole squared is n minus 1 times identity matrix. So this is n minus 1 times identity matrix plus identity matrix. So this is n times identity matrix. Same thing over here. So overall, we have n times identity matrix. This means that since Mn squared is n times identity matrix, we can use this to observe that all the eigenvalues are either square root n or negative square root n. That is not so hard to see. And Mn is a signed adjacency matrix of Qn, which is the adjacency matrix. So all the diagonal entries are 0. So the trace of Mn is 0. And the trace is also the sum of the eigenvalues. So we have a bunch of plus square root n and minus square root n adding to 0, which means that there has to be exactly half square root n's and half minus square root n's, which means there are 2 power n minus 1 square root n's and 2 power n minus 1 minus square root n's. So which means the 2 power n minus 1th largest eigenvalue is square root n, which is what we wanted to show. And this completes the proof. Right? Any questions on this?
Subrup, is there any relationship between the signs? This is a signed adjacency matrix, right? Any relationship between the signs and the corresponding parity of the subset? Because it seems like the columns are just orthogonal here. That's why we are getting Mn square equal to Ni.
That is correct.
So
yeah. So the signing actually makes the columns orthogonal. So your question is there a relation between the, so I can actually, I didn't make a slide on this, but I can tell you, so if you look at what happens here, like the definition of Mn, the recursive definition of Mn. So it is edges that we are signing, right? And edges go between two vectors of Hamming distance 1, right? So if the edges go in this part, the minus n minus 1 part, you give it a negative sign. But this is recursive. So all that we have to observe is when does an edge go into this part? And it turns out that, so you can write an edge as going from, let's say, V to U, right? Where V is a vector of the form V1, 1, V2, and U is a vector of the form V1, 0, V2, right? Because of Hamming distance exactly 1. So it turns out that we assign such a such an edge a negative value if and only if the parity of V1, that is the prefix before the change, has the parity of V1 is odd. So there is a way to see it. There is a characterization for this based on the edges. Is that what you were looking for?
Thanks. Yes, thanks, Subra.
Yeah.
Thanks.
Right. So I'll say a bit more about how or what prompted Huang to come up with this proof. And here I have this slide about how we can avoid the interlacing theorem. So I don't want to explain it in detail, but the key idea is that, so it's the same matrix, same signing, everything is the same. Just that the interlacing argument is replaced by a lower level argument. So basically, the point is that you can write, since it has square root n, it has 2 power n minus 1 eigenvalues with multiplicity square root n, then there is a matrix where you have of size 2 power n by 2 power n minus 1, where all the columns are the corresponding eigenvectors. And you can look at the subcollection, you can look at a row-wise subset of this matrix, or a row partition of this matrix, where the entries come from only those vertices that do not belong to H. And using this, you can construct a vector Y that turns out to be an eigenvector for H with eigenvalue square root n. And the only kind of non-trivial rule that we use here is that a system of equations, a system of homogeneous equations, 2 power n minus 1 minus 1 homogeneous equation with 2 power n minus 1 variables, there are one more variable than the number of equations, has a non-trivial solution. So, this, if you go, Donald Knuth wrote this proof, this variant of the proof. After there was an online discussion about this proof, Huang's proof, in Scott Aronson's blog, and there was a commenter by the name Shalev Ben David. So I think he's a computer scientist as well. I'm not sure where and if he's a student or faculty, but so he made this observation, and then Donald Knuth wrote it up, and it's there in the PDF. So I can share the link to this if someone is interested. Okay, so you can avoid the interlacing theorem by using simpler techniques. And this is related to what Aditya observed just now. Another explanation of why this signing works, right? So there is this inequality called Hadamard's inequality. So for an M by M matrix, the determinant of the matrix is at most, or the absolute value of the determinant is at most the product of the norms, with equality being achieved if and only if all the rows are orthogonal to each other, right? So, so one simple example is if you take a rectangle or a cuboid, or a parallelogram or a parallelepiped, the product of the side lengths is an upper bound on the volume, So the volume corresponds to the determinant, and the product of the side lengths is what we have on the right-hand side. And we know that in a cuboid, this is equal, and also the edges are orthogonal to each other. So things we can observe is that once we understand that we need, or we can try a signed adjacency matrix, and that might help us with the proof. The way one can think is that if you are looking for a signed adjacency matrix, Hadamard inequality gives us that the determinant of the signed adjacency matrix is at most square root n times square root n power 2 power n. Why? Because each row vector has exactly n ones and has norm square root n. And if you want the largest eigenvalue to be at least square root n, which means the first 2 power n minus 1 eigenvalues is at least square root n. And because the matrix is, the graph is bipartite, the spectrum is symmetric. So we also have 2 power n minus 1 negative eigenvalues with absolute value at least square root n. And hence the determinant is lower bounded by this quantity. And hence, if we want both of this, we have to meet it with equality. And hence, we have to have that the rows, all the rows are orthogonal. And once all the rows have to be orthogonal, it's just some trial and error like there in the slide. So you can you appeal to the inductive m-1 being a matrix of desirable of the desired property, and you can write a block a matrix with blocks like this B, K, K, C, and then you can easily figure out that it has to be like this. And this is unique, except for flipping the entries of, or flipping the signs of all the entries in a row and column, because that doesn't really change anything. Okay, so this is something that is straightforward to see. And this is probably how Ryan came upon this proof, or this particular sign. Any questions till now? I will move on to how this is relevant. As I said, till now, it looks like we are solving a combinatorial problem and not seemingly related to the computer science. And so how is it related? So let's define sensitivity. So before that, let me define Boolean function. A Boolean function is a function on the hypercube where each vertex of the hypercube is assigned a Boolean hypercube is assigned a 0, 1 value. Okay. So sensitivity is, so first let me define local sensitivity. So if you look at x and fx, the function at x, now if you flip one bit of the input x, does the output value change? Right? Does the value of fx change? So x superscript I denotes the vector x where the ith bit is flipped. Okay, so does the function value change? So what are the number of indices upon whose flipping the function value changes? This is called the local sensitivity at x. And the sensitivity of f is the maximum amongst all the local sensitivities. Okay, so just to see some examples, AND function. If you take the all zero vector, so assume n is at least 2. All zero vector, if you flip any bit, the function value is 0, and of 0 is 0. If you flip any bit, the function remains 0. So which means the local sensitivity of the AND function at 0 is 0. And the AND function is 1 only at the all ones input. And at the all ones input, if you flip any bit, the function value changes to 0. Which means the local sensitivity is n at the all ones input, and hence the sensitivity is also n, because sensitivity cannot be more than n. So OR function that has local sensitivity n at the all zeros input, it's very similar to the AND, and hence sensitivity is also n. If you take the XOR function, whichever x you take, flipping of any bit results in changing the function value. XOR is same as parity. So the sensitivity of the XOR function is n, local sensitivity of XOR function is n everywhere, and hence the sensitivity of XOR function is also n. Just to consider a different function like x1, which is a dictator function, fx depends only on the first coordinate. Obviously, this has this sensitivity and sensitivity 1, because if you flip the first bit, the function value changes. Right? Okay, now I will define what is called block sensitivity. A block sensitivity is similar to sensitivity, but in sensitivity, we allowed for flipping individual bits. In block sensitivity, we allow for flipping a set of input indices. So we want to consider a set of disjoint blocks B1 to Bk, such that if you flip all the bits in any block, B1, B2, any block, if you flip all the bits in one of these blocks, the function value changes. Okay, so the local sensitivity is the maximum way in which we can divide the n indices into blocks, such that, again, we don't need all the indices to be part of any block. Some of the indices could be left out. But at each block, the property that we want is that the flipping of all the inputs of that block should result in flipping of the function value. And what is the maximum number of blocks in which we can do this? That is called the block sensitivity. And that is called the local block sensitivity at an index. And the block sensitivity is analogously defined as the maximum of all the local block sensitivity. So x superscript bi means the vector x obtained by flipping all the coordinates which belong to the block bi. So the blocks need not be contiguous, although they should be disjoint. Fine. Okay. So some small observations. One way to consider blocks is to consider singleton blocks. But if you restrict yourself to singleton blocks, you're exactly talking of sensitivity. So the sensitivity is a lower bound on the block sensitivity, always. And obviously, the maximum number of blocks that you can get anywhere is n. Hence, the upper bound of sensitivity as well as block sensitivity is n. And if the function is non-constant, the lower bound is 1. Right? And we saw that AND, OR, and XOR have sensitivity n. And therefore, it must have block sensitivity also n, because you cannot have anything more than n. So the question really is about sensitivity conjecture. The question really is, can we upper bound block sensitivity in terms of sensitivity? So here we have a lower bound that block sensitivity is at least sensitivity. Can we get an upper bound for block sensitivity in terms of sensitivity? And this is the conjecture that was made by Nissan and Szegedy in 1992. They said that block sensitivity is at most polynomial in sensitivity. In other words, that's a constant such that block sensitivity is upper bounded by sensitivity power a constant. And what we know is that block sensitivity is lower bounded by the sensitivity. Is the conjecture clear? Is the definitions of sensitivity, block sensitivity, and the sensitivity conjecture clear? Just have a bit of water. Okay. And
so the lower bound which you mentioned, that sensitivity lower bounds the block sensitivity. This is just trivial, is it? You just define the blocks as the place where the function flips when you flip the bit.
Yeah. So if the function flips at k coordinates.
Yeah. So those are your blocks.
So I can make the blocks like these singleton sets.
Right. Yeah. Exactly. So it's just trivial to see that sensitivity lower bounds the block sensitivity.
Right. That's observation. Yeah.
Yeah. Sure.
Any other questions? Your slides probably can make one go too fast. So feel free to ask questions. All right. Yeah. You can interrupt me anytime. So why is it interesting, and a bit of history? This started from the works of Cook, Dwork, and Reischuk. I think they, in the early 80s, I think this is the journal version in 86. So they looked at the screw param machines, which means it's some parallel machine where machine model where you can read parallelly, but the writing is separate, is done exclusively. And the number of steps they were studying the number of steps to compute a function in such a model. And they showed that this is lower bounded by log sensitivity. And that's the first paper where they talked about this. And later Nissan showed that the crew of f, the minimum number of steps required to compute f in this model is actually tightly related to the log of the block sensitivity. So, and later Nissan, in the same paper, Nissan and as well as Nissan Segeti, they showed that the block sensitivity is also related to a bunch of other complexity parameters, right? And that is the history. And the point is that the other parameters that I was talking about are things like decision tree complexity, which means you can write f as a decision tree. So is the first bit 0 or 1? And then you ask, if the first bit is 0, you ask, is the second bit 0 or 1? If the first bit is 1, you may ask, is the fifth bit 0 or 1? So you can make a decision tree that computes the value of f. So the complexity of the decision tree is the height of the decision tree. And what is the decision tree with the lowest complexity? Similarly, another way to represent a function is as a degree over the real field. Now, like for instance, the AND function is nothing but, let's say AND function on 3 variables is nothing but x1, x2, x3. It's of degree 3. I can write a 3-degree real polynomial to represent the AND function. Even the OR can be written as a real polynomial, right? So another measure, complexity measure, is the degree, right? And so on. And what was known about before this, the resolution of this conjecture is that all these parameters are polynomially related, which means if you take any of these parameters, it is lower bounded by a polynomial on any other parameter and also upper bounded by a polynomial on any other parameter. Except sensitivity remained an outlier. Until the resolution of this conjecture, sensitivity was not part of this group. And with the resolution of this conjecture, sensitivity also gets to be part of this group. It is kind of surprising because one may think that sensitivity is kind of the more natural measure of complexity than the block sensitivity. So it's surprising that this conjecture remained open for so long. Right. So this is the history. So now I want to talk about a specific function. So I just showed examples of functions, but all of them, the sensitivity was equal to block sensitivity. Now I'll show you a function where the block sensitivity is quadratic in the sensitivity. This is called the Rubinstein function, and it will be helpful to think of the as a function on n² bits because it's easier that way. So the function is an OR function. You can think of the n² bits as laid down in an n by n as n rows, each row containing n bits. And the function is the OR of the g function on all of the rows. And the g function is equal to 1 if and only if 2 consecutive entries are 1 and all the other entries are 0. So below I have drawn a picture. So where n is 4. So each row, it does not fit in this way. It does not fit this characterization of G, or does not fit this definition. None of the entries are 1, so the G function is 0. For the first row, second row, third row, fourth row, and hence the F is the OR of all these rows. Hence F is also 0. Right? So this is the function on all zeros. And the block sensitivity of the function at the all 0 input is actually quadratic in n. Why is it? So recall this function is on n² bits, but it's quadratic in n. Why is this the case? So consider this flipping of 2 bits, the first 2 bits. Now the first row gives the output G equal to 1 because 2 consecutive entries are 1 and the remaining entries are 0. And hence the OR of these G's also give you 1. Now, if you consider the next block of 2 bits, even for this, the first row returns 1, and hence the OR of all the rows return 1. Now, if you look at the next 2 bits, and you can keep doing this, the second row now returns 1, and hence F returns 1. So the point is that if you flip any of these 2-bit blocks, the function value flips from 0 to 1. And hence the block sensitivity is at least n squared by 2, right? Because there are n squared bits here. So it's n squared by 2. Fine. Okay. And now we'll see that the sensitivity is linear in N. Let's see why. The function, so there are 2 cases. The local sensitivity when the function is 0 and the local sensitivity when the function is 1. If the function is 0 at x, then each row must output 0, right? Because the function is an OR of the outputs at each row. So now, if a row has to output 0, and what is the maximum number of sensitive coordinates it can have? It turns out to be 2. That's exactly when the row looks like this. All zeros except for 1, 1, and all zeros except for 3 consecutive ones. And in either case, the red bits indicate the sensitive bits. And for each row has at most 2 sensitive bits. And hence, overall, over n rows, we have at most 2n sensitive bits. So when fx is equal to 0, the maximum number of sensitive coordinates is 2n. When fx is equal to 1, if there are 2 rows that output 1, then the function is not sensitive, because even changing any entry at any row keeps the other row unchanged. If exactly 1 row outputs 1, then it is possible that all the entries in that row are sensitive, and hence the sensitivity is at most n, because of all the entries in that row. No other row is going to be sensitive. Hence, in either case, when fx is 0 or fx is 1, the sensitivity is at most linear in N. And we saw that the block sensitivity is at least quadratic in N. Hence, we have a function where the block sensitivity is quadratic in and sensitivity is linear. So this tells you that the constant C in this conjecture cannot be smaller than 2. It has to be 2 or more than that. Right? Okay. Any questions? And this is the history of what was known before the resolution of the conjecture. The previous upper bounds for block sensitivity in terms of sensitivity were all exponential. So it's exponential in 4, e, 2 here. And the lower bound is the Rubinstein function is what I showed you. In fact, the actual function is a bit different than what I showed you, but it's roughly the same. And all the gaps that were known between sensitivity and block sensitivity, these are the best. So the best gap was quadratic, and the best upper bound was exponential. And what we'll see is that the resolution gives a block sensitivity is at most sensitivity power 4, a fourth power upper bound. Okay, so we'll see why that is the case. So this is because of an equivalence relation that was proved by Gottsman and Daniel in 1992. They showed that consider real function h, small h. Now they said that if for any induced subgraph of the n-dimensional Boolean hypercube, which has number of vertices that is not equal to 2 power n minus 1, which means it's not an exact half partition, the maximum of the degrees of h, maximum of the max degrees of h and the complement graph, if it is at least hn, where h is this function, then we have that sensitivity is lower bounded by h of the degree. So this degree is the degree as a real polynomial, the complexity measure that I spoke about earlier. Okay, so they said that if sensitivity is, these two are equivalent, is what they show. And for the for us to prove sensitivity conjecture, the latter is enough, because degree is anyway polynomial related to block sensitivity, and this gives an upper bound for block sensitivity in terms of sensitivity, because the block sensitivity is already upper bounded by degree squared, which was also proved by Nissan and Segeri in the same paper. So if we can show that sensitivity is at least this, then we would have shown that block sensitivity is upper bound by a function. So h has to be a function that is chosen appropriately. And we already, so if we show the red part, right, that implies that block sensitivity is upper bounded by this function. And we know that by the discussion in the first half of the talk, for any induced subgraph of size 2 power n minus 1 plus 1, the max degree is at least square root n. So which means the h function is square root n. So h inverse is the squaring function. So that gives you the square of the square. So sensitivity power 4 upper bound. So again, just to summarize this, if 2 power n minus, this is what we showed at the beginning. With the equivalence, we get that sensitivity is at least square root of the degree of f. So this degree, again, there are two degrees. This degree is a degree as a polynomial, not the graph degree. Yeah. Was there a question?
Yeah, so Brooke, so this lower bound, so the conjecture is proved, but the bound may not still be tight, right? In terms of
the bound is still not tight, correct. So because the lower bound, the gap that we have is squared, right? And what we have seen is that block sensitivity is quadratic, fourth power in sensitivity, upper bounded by fourth power in sensitivity.
Okay, sure.
In fact, this 2 factor is actually not there. Later, it was shown that block sensitivity is at most degree squared. But yeah, I didn't want to put that reference.
Okay, sure.
But still, the quadratic versus fourth power, that gap is still there.
Okay, sure.
However, one remark that I want to make is that the sensitivity is lower bounded by the square root degree of f. This relation is tight. The relation between sensitivity and the degree, this is tight. If you consider the and of R's function, so if you have a function on, let's say, n inputs, where n is a perfect square, so consisting of root n rows, and we take the r of each rows and the and of the r's, we get the and of r's function. In this case, the sensitivity is square root n and the degree is actually n. So the corollary that we obtain here is tight. However, the resolution of the sensitivity conjecture still remains some gap.
What about the relation between block sensitivity and degree? Is that also right? Independent?
I have to check. I'm not sure.
Okay, sure.
Yeah, there is a survey by.
For a bit. Sorry, previous slide for just a bit.
Previous slide. Okay.
Yeah. No, I don't have a question. I just want to see this for a bit more, so you can just continue talking.
Sure.
Okay. Yeah.
So the point is that this relates this combinatorial problem to the sensitivity and block sensitivity. Yeah.
So again, this degree was the degree as a polynomial.
As a real polynomial,
right?
Yeah.
So that's just the degree of the Fourier expansion.
Yes.
Right?
Yes.
So wait, the degree is the -1 + 1 degree of f, or the 0, 1 just?
Aren't those the same? They're the same.
The same?
Because
Okay. Okay, it's linear, right? Okay.
Yeah, it's linear conversion.
Yeah. Any other questions? Should I keep this slide? So I may go on for maybe another 5 to 10 minutes more, and I will stop after that.
No more questions from me.
Yeah, sure. So what we showed in the beginning of the talk is the red part with hn equal to square root n. So the function was square root n. And this proves that sensitivity is at least square root of the degree of f. Right?
So Subruk, one question.
Sure.
So the example that you had shown for the upper bound at the start of the talk on the induced subgraph having degree at least square root n.
Okay.
So does that give us an explicit function here via that Gaussian linear conjecture, which has any of these equalities? I mean,
So we showed we saw a subset of size 2 power n minus 1 plus 1 with
right,
degree square root n. Yes.
with square root n. And now if you go back to the previous slide of the conjecture,
Huh.
so if you run it through that, does that imply the existence of some Boolean function f where s of f is equal to h of degree of f, where h is square root n? Is that? I'm just trying to parse the examples whether it maps or maybe
So I have few slides on the Gaussian linear equivalence, but
okay.
this particular question I'm not sure. But as far as this bound being tight, I already told you one example, right?
Right. Okay.
And of course function gives you such an example.
Okay.
So again this if I it's not clear to me now.
Okay. No, I was just wondering, is there a relation between that tight example and something which gives the tightness over here? I forgot that you mentioned the and of course already gives you something tight.
Sure.
Okay.
Okay. So the next few slides are the Gaussian linear equivalence, how that comes about. Even this is like a very short proof, but I don't want to really go through this proof.
Just 1 second, Subruk. So, can you go back to the Gaussian? Okay, I think it's here, Gaussian linear. So, but still, it's not clear to me that you prove the hypercube question then from, this maths degree of delta or qn minus h delta. Basically the larger of the two you can take maybe. Maths of degree of the larger of the two.
So you're asking how the Gaussian linear equivalence implies the sensitivity?
Yes.
Okay, so let me tell you why that is the case. So I'll just remain in this slide. We already had a proof that for any graph on 2 power n minus 1 plus 1 vertices,
yes,
it contains a vertex of degree square root n.
Correct.
So if you take any unbalanced subgraph, unbalanced means the size of the subgraph is not half, 2 power n minus 1.
Yes.
So then either h or its complement
got it. Yeah.
has more than half, and hence if you look at just the subgraph, the max degree can only go down, and even the subgraph has square root n degree.
Yeah.
Right, because this follows because
okay. H of okay.
So we showed that in a graph of 2 power n minus 1 plus 1 vertices, the max degree is square root n. But even if you take any unbalanced partition, either h or the complement has more than half, and whichever part has more than half has a subgraph of 2 power n minus 1 plus 1 degree of 1 vertices, and that has square root n degree.
Okay.
Right, and that implies that sensitivity is overbounded by the square root of degree of f, and that gives us what we want.
Okay.
Okay, so this equivalence, I'll just very briefly explain this. This equivalence, so in fact, we don't need the equivalence. We just need 1 implies 2. And it's a bit more convenient to go through 1 or go through 3. So, and you can see that 3 implies 2 because so 3 is the same as 2, but when the function is restricted to full degree functions. Why does 3 imply 2? 3 implies 2 because you can consider any function f that is not full degree. Now you look at a monomial, a max degree monomial of that function. And if you restrict your focus on that, on the hypercube created by that max degree monomial, now you can apply 3 on that restricted function. You can apply the third point, and you get that sensitivity of that function of the restriction is at least Hn. So now that means h of n meaning h of the max degree, and therefore you get 2. So 3 implies 2 is trivial, is not that easy to, not that difficult to see. 1 implies 3 takes a bit more work. So essentially what happens is, if you look at this figure, what we have here is the OR function. If you look at this figure, so OR of all zeros is 0, so red is 0 and green is 1. And the core idea of the equivalence comes because if you flip the value of the function at the odd parity vertices, so now if I'm going to flip, so now all the odd parity vertices turned red. Earlier only the origin was red. So now if you look at the graph induced by the red vertices, the max degree of the graph induced by the red vertices is actually the sensitivity of the graph, sensitivity of the function. So this is a function, and when you flip the function value at the odd parity vertices, you get and look at the induced graph induced by the red vertices, you get a vertex of degree 3. And this vertex of degree 3 exactly corresponds to a point of sensitivity 3, local sensitivity 3 at the function. And this forms the heart of the proof, the heart of the equivalence. So here, the collection of red vertices was a most sensitive bit. If the most sensitive bit was from the green vertices, then the max degree vertex would have been from the green vertices. So the rest of it is, even the Gaussian linear proof is very short, but since we are kind of out of time, I don't want to explain that. Yeah. I'll just quickly, if any students are listening, I'll just quickly just walk through this timeline that Huang wrote in Scott Adamson's blog. So it could be a bit inspiring for everybody, in fact. So he first heard of this problem in 2012 when he joined for his postdoc. So I think he graduated his PhD in 2012. And what strikes me, what is most interesting, most striking is the last part in 2013 to 18, that he kept trying to attack this problem whenever he learned something new, right? So this and many of the discussions that I've read focus on how he got this proof, because it's so simple and he has eluded so many brilliant minds for so long, right? And it is just that his persistence has paid off. Of course, he's brilliant, smart, but he has also been incredibly persistent through the years, right? And yeah, so this I thought I will share. And another point I just want to mention is couple of places I read that there's a step that seemed to be most didn't come naturally to most people, or most people didn't think of naturally, was the taking the signed adjacency matrix. So most of the other tools were kind of standard, but the signed adjacency matrix, even though it was a kind of a standard, it's an easy proof to see, but it's not a trick that came to people automatically. So many people I saw that they refer to this as the step that seemed to not come to people so easily. And some open problems, so some of these are there in the paper. So first one has already been mentioned, the gap between the upper bound and the lower bound is still open. So another problem is, now if you want, instead of square root n, if you want to go to a subgraph where you're assured of max degree being at least n power 0.6 or 0.7, how many vertices will you have to take? So for getting square root n degree, it is enough to go to 2 power n minus 1 plus 1 vertices. For getting n power 0.6 degree, how many vertices do you have to take? Again, as I'm speaking, one possible approach may be to play around with the signings of the matrices, if you're just following this paper, and try to find some signings so that so that the appropriate eigenvalue of Qn itself is large, much like what we did in this paper. Another problem, there is some progress on this problem by Alon and Zheng earlier this year. Can we get such bounds? So alpha is the independence number. In the Boolean hypercube, the independence number is exactly 2 power n minus 1, exactly half the vertices. So the degree of alpha of the Boolean hypercube plus 1 was shown to be at least square root n. Right? So now, can we say such things for other graphs? So for some Cayley graphs, Alon and Zheng, they considered what is called a variant of the signing. They called some unitary operation, unitary signing or something like that, where they multiplied the entries of the adjacency matrix or something, and they got, for some Cayley graphs, they were able to kind of port Planck's proof to any Cayley graph G. But that question still remains. Can we say that in other settings? Yeah, I think that's all I have to say. I just want to leave with the proof was summarized by Ryan O'Donnell in a tweet. So I just want to leave you with that. Thank you.
He's actually written it like an exercise.
Right. Yeah. Any other questions?
Yes, good. So the bound for general graphs we want in terms of what?
No, the alpha is the independence number. So what we showed was for Boolean hypercube, where G is the Boolean hypercube, we showed similar as in square root n bound. Right? We showed a square root n bound.
So I mean, but bound need not necessarily be in terms of the number of vertices, or in terms of, yeah, it's not clear what the bound should be in terms of, right?
Yeah. So yeah, maybe it's a bit of a vague question, but yeah, there is some. I think Alon's paper that I mentioned that through square root n bound for some Cayley graphs. Yeah.
But I think, yeah, probably Cayley graphs may have, I mean, some linear algebraic structure, right? Compared to general graphs.
Yeah. Yeah. So it's a bit vaguely stated. Yeah. This particular open problem was mentioned as an open problem in the paper itself.
So could there be some relation to combinatorial, like this vertex expansion or edge expansion, because they are also related to eigenvalues, and yeah, I mean, intuitively we can think that high expansion should imply something like this.
Yeah, I guess yes, but the signing kind of makes it.
I mean, yeah, not this technique. Yeah, I think, yeah, for this technique,
there could be relations between edge expansion or vertex expansion and this. Yeah. Any other questions?
Yeah, thanks, Subra. It was a nice talk.
Thank you.
Yeah, that's all. Thanks, Subra, for a very clean presentation.
Thank you.
Yeah. Nice talk, Subrahmanyam. Thank you.
Yeah, I don't know how to clap online. Just one irrelevant but independent thing, that I actually reviewed a thesis, a PhD thesis on the sensitivity conjecture.
I see. Okay.
When I went for the defense, I asked the PhD candidate, do you think we'll make any significant progress on this problem anytime soon? And he said, no, sir, this is very hard. I don't think we'll make. 2 months later, Huang's paper came out.
Right.
And it was
such a simple proof has avoided, like, nobody was able to spot it.
Yeah.
So whose thesis was it? Did you review?
Dinesh Jailal's student.
Oh, okay.
His thesis is on this.